Okay guys, we're going to do the second part of the notes here today. Tomorrow our plan is to start the problems from the section, but today we'll just finish these notes and there'll again be a short quiz after this just to see how you're doing, and if you have any questions, post them in the message boards on Moodle. Alright, so buoyant force. Buoyant force is when if you put something in water, for example, it's the upward force that counteracts gravity. And so it's always going the opposite direction of gravity. And the force is equal to the weight of the fluid that is displaced. So for example, if you put a boat into water and the boat weighs 10 newtons, in order to float, it's going to displace 10 newtons of water. So it's going to push 10 newtons of water out of the way. Or if you drop something into water, let's say you drop like a block of iron into water and it weighs 10 newtons, it's going to displace some water less than its own weight. So it might displace 6 newtons of water, and then that means the buoyant force in it would be 6 newtons. And the equation for buoyant force is the buoyant force equals the density of the fluid times the volume of fluid displaced times gravity. Or you can also do it the mass of the fluid displaced times the mass or times the acceleration due to gravity. And for a floating object, the buoyant force is going to equal the force of gravity on the floating object, which is different than the force of gravity on the displaced fluid, which was the above equation. So this is a demonstration of Archimedes' principle in buoyancy. So we have a 7-pound weight of some kind. We put it into water. The weight displaces 3 pounds of water. So push 3 pounds of water out of the way, and like would have spilled out of that container right there. That means the buoyant force in it is 3 pounds up. So that means the new weight of the object in the water, the apparent weight of it, would be 4 pounds. So again, just to reiterate, the weight of the displaced water is equal to the buoyant force pushing up on it, which cancels out that much of gravity. Alright, so some buoyancy questions. If the buoyant force in an object is less than the force of gravity, what's happening to that object? So if the buoyant force is less than the force of gravity, the object is sinking in the fluid, or in the water, if you want. That's easier to think about. Number 2, if the buoyant force in an object is greater than the force of gravity, what's happening to the object? In this case, if the buoyant force is greater, that means the object is floating. Alright, so number 3, objects that are denser than water sink. So how is it possible that a steel boat can float? So the real key here is not that objects are denser than water that sink, it's if they don't displace water equal to their own weight. So for example, a steel boat is shaped so that it displaces enough water to counteract its weight. So if you just took a chunk of steel, it would not displace enough water to counteract its own weight. But if you shape it into a boat shape, now it's going to displace more water, and it'll displace enough water so that it displaces a weight of water greater than or equal to its own weight without going totally under the water. All right, Pascal's principle is that pressure is transmitted to every point in a fluid and to every point in a container. So this is useful for hydraulic lifts. So basically the pressure at one point is equal to the pressure at the other point. So in a hydraulic lift, which I'll show you here, the pressure at the input force, so you have a small piston right here, and that small piston is going to have an input force, and that's going to apply an output piston to the output force to the larger piston right here. The larger piston experiences a much greater force because it has a much larger area than the smaller piston. So if you push down with 10 newtons right here, you might have this upward force being 100 newtons. I did that with my left hand, you should be proud. How that force comes about is this input force. The smaller piston goes down a much longer way than the big piston goes up. So the small piston will go down a short distance, and the big piston, small piston will go down a large distance, and the big piston will go up a short distance. But the force that the big piston applies up ends up being much greater than this force that you need to apply on the small piston to push down. So if you took POE last year, it's a lot like mechanical advantage. You're sacrificing distance, so the big piston doesn't go up as much, but you get an increase in force. So hydraulic lift questions. How does the force on the large piston apply as compared to the force the smaller piston? So the larger piston applies a much greater force, but it goes a much shorter distance. So we get to the next slide. All right, and again, this is a question I just answered. So number 2 says, how does the distance the larger piston moves compared to the distance the smaller piston moves? The larger piston moves a much smaller distance than the larger piston moves a smaller distance than the smaller piston. So the smaller piston, larger distance, small force, large piston, small distance, big force. All right, the last section here is fluid flow, and we'll go into Bernoulli's principle as well. So for fluids in a pipe, the amount of fluid flowing by a certain point every second must be equal to the volume per second at every other point in the pipe. You can't have like a gallon per second going through one part and 20 gallons per second going through another part in the same pipe. You get like a buildup of water, and that can't happen. So the equation for that is volume 1 over time equals volume 2 over time. You can also rewrite that as the area of point 1 times the velocity of the fluid at point 1 equals the area of point 2 times the velocity at point 2. That means the speed of a fluid in a pipe depends on the cross-sectional area of the pipe. So here's an example of a pipe here. At point 1, you have a large area, which means it's going to be moving much slower. Once it gets to the smaller area, A2, the velocity goes up and speeds up in order to keep the same amount of water flowing through both pipes, flowing through both parts of the pipe at the same time. So again, the volume per second at each point 1 and point 2 here, has to be equal, so the smaller area needs a bigger velocity in order to keep the same volume per second flowing through it. An example of this is if you've ever taken a hose in your backyard, you put your thumb over it, you decrease the cross-sectional area, the velocity that the water comes out there with has to increase because you've decreased the area and to keep the same amount of water flowing through the pipe, and that's why it shoots out much further when you put your hand over it. You've increased the velocity of the water coming out by decreasing the area. So question number one says, when a pipe gets narrower, does the speed of the fluid in the pipe, that should say, I'll fix that, increase, decrease, or remain the same? The speed of the fluid in the pipe will increase when the pipe gets narrower. All right, Bernoulli's principle. The faster a fluid flows, the less pressure it exerts on things it comes in contact with. So, for example, this is how airplanes fly. The shape of the wing causes the air to move faster over the top. That creates low pressure on the top and high pressure on the bottom. And the faster the plane flies, the bigger that difference in airspeed and the bigger the difference in pressure, so the more lift is generated. And that's true of anything. You can try this experiment at home. If you blow across the top of a sheet of paper, you'll see the paper lift up, because when you blow across the top, when you move the air faster across the top, it creates low pressure on top, and the high pressure on bottom will push it up. So last question here. If a pipe gets narrower, does the pressure exerted by the fluid on the sides of the pipe increase or decrease? So in this case, the pressure is going to decrease because the fluid is flowing faster through the narrow part of the pipe. So if you narrow that pipe, the pressure on the sides of the pipe ends up decreasing because the fluid is flowing faster, which means less pressure is being exerted. All right, that's the end of the notes for today. If you guys have any questions, again, post them to Moodle. And if you're having trouble posting to Moodle for any reasons, you can feel free to email me as well. We're going to start problems tomorrow, and hopefully everything is going okay for everybody. Let me know if you have any problems other than physics as well. We will talk to you tomorrow, I guess.